Hi, my name is Ethan Weeks. I am a senior in mechanical engineering here at UW-Platteville, and I was last year's team lead for the Argonia Cup competition. For Argonia Cup 2026, Pioneer Rocketry is bringing lessons learned from last year into our design this year. During Argonia Cup 2025, our fin can section of the sustainer separated due to using blue Loctite, which corroded the aluminum aero pack, which allowed the eye bolt connecting the two sections to loosen and eventually separate. Upon further investigation into the rocket's failure, we discovered two additional problems. We realized that we had used far too small of an igniter for our sustainer, meaning that it had zero chance of igniting overall. Also, we discovered that we had accidentally caused our Fluctus computer to have a critical failure, which caused it to fail at firing any of the charges. Compiling all of our failures, we left the competition with a lot of wisdom on how to improve for Argonia 2026. Using those new lessons, this year, Pioneer Rocketry will head to Kansas with our strongest competitor yet.
Hello, my name is Grant. I'm a junior majoring in mechanical engineering. I am the team lead and club president. Upon extensive research into our failures in Argonia 2025, we have made some major changes to ensure our success. To fix the issues with the fin can, we consulted with many current and former members of the club. After discussion, we implemented a design that a former member created. Our interstage coupler has been improved to securely retain the sustainer while allowing the booster to drag separate. In order to give the second stage the best possibility of lighting, we will dip our firewire electrical match in Procast. Procast is a highly energetic compound used to assist in lighting the motor, allowing our sustainer to successfully ignite and bring our team to victory. Additionally, we designed an expansion cone to squeeze every bit of performance out of our rocket motor, further ensuring that we have a strong and competitive design. To resolve our problems with the Fluctus computer failing, we have recoded our system to ensure that it can single-handedly fire and deploy all charges. Through multiple test flights, we have proved the Fluctus's capability with a 100% success rate. For redundancy, we will also install a Raven 4 as a backup flight computer in both stages. With these revisions and innovations of our rocket, Pioneer Rocketry is a strong contender for first place at Argonia Cup this year.
My name is Daniel Whitty. I am majoring in mechanical engineering, and I am the design lead for Argonia Cup 2026. To start our design this year, our team decided to have every member provide their own design. Upon discussion, we identified the best overall rocket while incorporating strengths from many other designs as well. We then used a continuous improvement philosophy to confidently say that our rocket was the best that it could be. The overall design consists of a 54mm minimum diameter sustainer, in combination with a 2.6-inch booster. We prioritized maximum altitude with minimum thrust, going through over a dozen variations of motor combinations, fin designs, rocket materials, and ignition delays. After we found a variant that exceeded competition limits, we filled it with golf balls until we were at the maximum possible score. For the sustainer, we went with an overall length of 6 feet and 10 inches, split into a 13-inch nose cone, an 18-inch payload section, a 48.5-inch motor and recovery section, finalized with a 2.4-inch expansion cone. Our current layout plans to carry a total of 14 golf balls to apogee with an Aerotech K270 motor. Our booster is 4 feet and 3 inches long, consisting of our interstage coupler, an 8-inch payload section, and a 42-inch motor and recovery section. This powerful first stage will launch our sustainer to maximum altitude with a Cesaroni Technologies K940 motor. To design the fins, we decided to use designs that had proved their effectiveness in the real world. We based both sets of 1/8-inch thick fiberglass fins off of the vertical stabilizers of various high-speed aircraft. The booster fins are based on an optimized combination of stabilizers from the X-59, SR-71, and Concorde, while the sustainer fins are based on the X-15, F-15, X-43, and XB-70. We finished off the fins with a mathematically optimized hexagonal cross-section.
I'm Colin Sutter, a junior studying computer engineering here at Platteville. For the Pioneer Rocketry, I am the head of electronics. The sustainer utilizes a Fluctus flight computer due to its ease in configuring pyro channel logic. For redundancy, the electronics bay also holds a Raven 4 as a backup flight computer, chosen because of its strong track record in flight and due to our club's prior experience with it. Our booster's primary flight computer is a Raven 4, used for the same reasons as in the sustainer. As a backup computer, we have an Easy Mini, a reliable computer for dual deploy rockets. In addition, the booster contains a GPS tracker, and both stages have an RDF beacon to assist in recovery. Overall, both stages of the rocket utilize precise flight computers to give us the best launch possible.
my name is Liam Wagner. I am a sophomore software engineer, and I am the head of R&D with Pioneer Rocketry. Our rocket required a long delay between booster separation and sustainer ignition. This delay was deemed long enough to potentially cause major issues mid-flight. To reconcile this, we decided to implement some strong staging logic, ensuring that we can salvage the launch in the event of a small mid-stage deviation. The basic idea behind the logic is to let the second stage coast for up to 5 seconds, and then ignite once the countdown finishes. However, in the event that our rocket's orientation deviates from vertical, the flight computer is ready to activate a preemptive ignition of the sustainer motor. If the rocket deviates anywhere from 15 to 20 degrees from vertical, our flight computer will automatically override the countdown and ignite the sustainer motor. As a precaution, the flight computer also checks to see if the rocket is traveling at a high enough velocity, that being 200 feet per second, to safely start the preemptive ignition. Another innovation to our design this year is that of our cable cutters. Based on Hapcat Rocketry's cat claws, our cable cutters are used to control when each of our parachutes will deploy individually, which is very helpful in a dual deploy rocket. With our rocket being over 11 feet long, a major concern was the amount of wiggling that it would do in flight. The cable cutters solved this issue by greatly reducing the amount of required separation points. In addition to this, the cable cutters will make the rocket far easier to recover by allowing us to deploy the drogue chute at apogee, and then deploy the main chute at a far lower altitude, reducing strain and wind drift during descent.
I'm Sam McKee. I am an electrical engineering major at UW Platteville, and my role for Argonia Cup is photographer, and I was also the former president of Pioneer Rocketry. To finish off the design of our rocket, we decided to have a single separation dual deploy system for descent and recovery. This means that both our sustainer and booster stages each will have a drogue chute deployed at apogee, and then the main chute will deploy at 1,000 feet by using the cable cutters. The booster will be the first to begin its descent, starting off the deployment of a 9-inch drogue chute, and then the cable cutters will release a 36-inch main chute. The sustainer will follow, releasing an 18-inch drogue at apogee, and then also using the cable cutters to release a 36-inch main chute at an altitude of 1,000 feet. Both of the stages will use 2 modes of communication to assist with recovery. The booster will be transmitting its location through a GPS tracker in addition to a radio direction finding, or RDF beacon. The sustainer is slightly more complicated, with it also using an RDF beacon, but using its Fluxus flight computer as a GPS tracker instead of a standalone transmitter. Overall, recovery systems will ensure that our rocket not only excels during its ascent, but also stays protected and efficient during its descent and eventual recovery.
Finally, our team made sure that safety has been and will continue to be the #1 priority. Throughout our entire build, we have made sure to use proper protective equipment based on the material at hand. We used various PPE, including N95 rated respirators, protective eyewear, nitrile gloves, as well as proper ventilation while working with fiberglass paint and epoxy. We have also followed rules and guidelines outside of the build room as well, specifically at our personal launch site. We always ensure that we are following the restrictions and rules of the FAA, NAR, and Tripoli, so that our entire team remains safe at all times. We also plan on prioritizing safety at the launch in Argonia as well. During our recovery, every team member will be given a handheld radio, as well as proper hydration and communication in the event of an extended recovery. Finally, we are also going to make sure that every team member has the proper outfit to be able to remain comfortable and safe during the recovery walk.
Overall, our team is ready to show Argonia Cup what Pioneer Rocketry is capable of. Through our failures in Argonia 2025, we have innovated and designed one of the strongest competitors for the gold at Argonia Cup this year. We worked extensively on our design, ensuring our electronics, logic, and recovery are the greatest they can possibly be. Our rocket is planned to reach 26,477 feet with 14 golf balls, giving us a predicted score of 92,528.28 points. With this in place, we are extremely confident in our ability to take a victory home to Platteville.
Thank you to Onshape for sponsoring Pioneer Rocketry.
Thank you to the Wisconsin Space Grant Consortium for helping with travel for this year's Argonia Cup.
Thank you to CMG for sponsoring Pioneer Rocketry.
Thank you, Oshkosh, for sponsoring Pioneer Rocketry.